So, this lecture is focused on a very specific concept, the concept of equivalent metrics and norms. Right? So the definition for metrics is over here. Suppose you have a set X and you have two metrics on X. Let me remind you what those are. Well, D1 takes as input a pair of points on X, in X, and as output produces a real number that's non-negative. So the distance, right, between 2 points in X is a non-negative real number is equal to 0 if and only if X is equal to X prime. It's also symmetric. And it satisfies the triangle inequality. So everything here holds for all X, X prime, X double prime in the space X. So this is a triangle inequality, right? And right, so we have these three properties. We assume that D1 is a function satisfying these three properties, and the same holds of D2. So there are two metrics on the same space X. They're said to be equivalent if they have this property. Take any sequence in X and any point, then X sub n converges to X according to D1, which really means D1 of X sub n to X goes to 0, because n goes to infinity, if and only if the same thing holds for D2, right? So equivalent metrics are metrics that agree on which sequences converge and what their limits are. If two metrics are equivalent, it means that they always give the same answers to these two questions. Does this sequence converge? And is the limit of the sequence the point X? Right. So equivalent metrics don't need to be the same metric. For instance, it's an easy exercise to notice that if I take a metric D1 and take D2 to be, say, 10 times the metric D1, meaning I just multiply all the distances by 10 or by any other fixed positive number, right? This will give me an equivalent metric. There are other things you can do which also give you equivalent metrics, and we're going to see some of those today. And the main point is that somehow, if you don't care specifically about the distances between points, but only about convergence of sequences, equivalent metrics are more or less the same for that kind of purpose, right? And I'm going to see that they give rise to the same topology on the metric space. So that's going to come up later when we talk about topology of metric spaces. Okay, so there's nothing really too deep that I want to tell you about these things here, except that I want to give you some examples and some exercises to work on later. And I'm going to prove a theorem about equivalent norms. So what are equivalent norms? Well, suppose that you have a vector space. We know that any norm of that vector space gives rise to a metric. And two norms are said to be equivalent if the metrics they give rise to are equivalent. So no big deal. Okay, but let's try to see the interesting things about this concept, right? So let me write down a fact here. Let's say that if we're talking about X, the real line, and D1 is the standard metric. And well, the standard metric, let me remind you, is that the distance between two real numbers is the absolute value of their difference. Okay? So now I'm going to give you a metric that turns out to be equivalent to D1. To define it, let me first define a function that maps the real line to the interval -1, 1. It takes t and produces t divided by 1 plus absolute value of t. And D2 of t and t prime is equal to the absolute value of the difference between psi of t and psi of t prime. So this is another way to measure distances. May look artificial. It's not that artificial if you think about what this function psi is doing. So basically this function, well, it has two asymptotes. Here's plus 1, here's minus 1. If you ponder a little bit, you realize that this function has a following shape. I mean, its graph has a following shape. What equals 0 at 0. For a negative t, it asymptotes to minus 1. And for positive t, it asymptotes to plus 1. In particular, something that's implicit in this graph is that this function is strictly increasing. And it particularly maps different numbers to different values. Well, that's related to the first property in the definition of a metric, right? The first property is that d2 of different points should be non-zero, and it's clearly true, right? The distances are, these values are always non-negative. If t is different from t prime, then because psi is a bijection, psi of t is different from psi of t prime, therefore this is non-negative. Well, symmetry is also true, right? Because if I flip t and t prime here, I just flip here. And the triangle inequality, well, I mean, it's really no big deal, right? So if you just, it basically boils down to the fact that t and t double prime, this is psi of t minus psi of t double prime, which is less than or equal to, by the standard triangle inequality of the real line, to the sum. Okay. So you see that this is the distance from t to t prime, and distance from t prime to t double prime, according to d2. Therefore, d2 really satisfies the axioms of a metric. And how do we know it is an equivalent metric? First of all, okay, there are a few things that I'm not going to prove here. One of them that I already mentioned is that psi is a bijection, right? It's actually not too hard to figure that out. It's just, you need just to compute the inverse function, right? And that you can do explicitly. So I'm not going to do it for you, but you can figure it out. Now, if you do it, you realize that psi and the inverse function of psi are continuous. And what does that give you in this context? It gives you that if a sequence Tn converges to T, then psi of Tn converges to psi of T. And actually it's an if and only if, right? Because it can use the inverse function, it's continuous. So you get this. And from this, you can see that the two metrics are equivalent, meaning that if the distance, meaning the absolute value of the difference between t and minus t, right, d1 of t and t, if this goes to 0, then the distance between these two guys, which is d2, right, the absolute value of the difference goes to 0, and vice versa. So the two metrics are indeed equivalent. And, okay, what's the whole point of this exercise, right? Notice two things. First of all, D2 is bounded, meaning that the D2 takes values between minus 2 and 2. Well, sorry, D2 takes values between 0 and 2. The distance between, remember that this function psi maps the whole real line to this interval. So D2 of 2 points is never going to be greater than the length of this interval. And another point that's really important, and that our D2 is not complete. That I'm going to leave as an exercise for you. Basically, what you do is look at a sequence over the real line that converges to infinity. Say just the natural numbers, 1, 2, 2, n. Well, it converges according to the standard metric, right? So if you look at the sequence 1, 2, 3, up to n, up to infinity, sorry, the values of psi of 1, psi of 2, psi of 3, psi of 4, they're going to converge to 1. And they're going to be a Cauchy sequence according to the metric D2, which doesn't really converge anywhere. So that's an exercise for you. To check that if you take their Cauchy sequences according to the metric D, well, sorry, there are sequences that are Cauchy according to the metric D2, which don't really converge anywhere. Therefore, this metric space here is not complete. Remember I told you, when we talk about complete metric spaces, that's not a property of a set. It's a property of a set with its metric. And what this is telling you is that really you can change the metric to an equivalent metric, right? You can change the standard metric to an equivalent metric and turn R with this new metric into a non-complete metric space. Okay, so far so good. Here's another exercise that I want you to think about. The exercise is this. So now take x equal to q or n, one of the two. D1, still the standard metric, so you could say it's the metric induced over these two sets by the standard metric on R. And D2 is the discrete metric. All right, so the pair of points is 1 if t is different from t prime, and 0 if t equals t prime. Okay. Prove that D1 and D2 are equivalent. Over n, but not over q. And what this is saying is remember that in order to converge according to this discrete metric, it's necessary and sufficient that the sequence you're looking at is eventually constant. So for all large enough n, it stays at the same place. It turns out that if you want a sequence to converge in the set of natural numbers according to the standard metric, that's also the property you need. It's related to the fact that this set is discrete. It's a discrete subset of the real line. And for Q or R, if you want, you can also have R here. Things are different, right? You can have convergence sequences that don't become eventually constant, right? So that's the property you need to look at to solve this exercise. And okay, now we have a theorem in this class, which is about equivalent norms. And what we're going to see in the exercises and later in the class, well, I mean, we've already seen an example of two equivalent metrics over the real line, where basically what I did was I took the real line and sort of shrunk it to fit into the interval from -1 to 1. And I said, well, now I get a new metric, and it's an equivalent metric, right? In particular, I took the whole line, which is unbounded, and turned it into something bounded. Now, with norms, you have less flexibility. So if you want two norms to be equivalent, there's a necessary and sufficient condition that's less obvious, that precludes this kind of example that I do. So, okay, what's the theorem? V vector space and we have two norms V1 and norm 1 and norm 2 are equivalent. if and only if, so we write that like this, there exists constants c and small c and capital C, such that for all vectors v, if I look at the norm of v measured by norm 1, and that measure and the norm measured by norm 2, so I have this. So it's like saying norm v2 is the same. Well, it's not equal to norm 1, but it can be the ratio between the two norms can be bounded above and below by positive constants, right? So the ratio never gets too close to 0, and the ratio never gets too close to infinity. This is what this is saying. One consequence of this is that all the LP norms on RD are equivalent. And this I'm not gonna prove in detail. This is again a nice exercise, so you should try to do it. Okay, so let's prove this theorem, and that's gonna finish this video. So one direction of this theorem is easy, and right. So let me write this with a double arrow because then I can write the proof of each direction separately. So I'm going to move first from this to this to show that if this condition holds, then the two norms give rise to equivalent metrics, or they're equivalent. Sorry. How does that work? Okay, I mean, it's really simple. Suppose you have a sequence of points and a limiting point, a potential limiting point, all in V. And if Vn minus V1 goes to 0, then you can see that the distance between Vn minus V2 is less than capital C Vn minus V1. So this guy is going to 0. This guy is sandwiched between 0 and something that goes to 0. Therefore, it also goes to 0. And how do you do the converse statement? Well, it's more or less the same, except that we have a different relationship, right? So we have this one bounded above by this one. But look, suppose that Vn minus V2 goes to 0. Now I can say that the one metric, well, I don't have capital C here anymore. But notice that little c times one norm is less than the two norms. So I can have 1 over little c here. And again, I have a sandwich, right? So between 0 and something that goes to 0. And therefore, I know that the norm 1 goes to 0. So I can go back and forth, right? There's something hidden here which is kind of interesting. Notice that this condition seems asymmetric, right? The role of norm 2, roles of norm 2 and 1 seem different, right? So it's saying norm 2 is sort of sandwiched between multiples of the norm 1, but it can turn this around. You can also write this again as saying, I guess, that V2, 1 over capital C, and I guess 1 over C, did I do this right? Yeah, this should be V1, and yeah, V2. So it turns out this relationship is symmetric, even though that's not completely obvious at first sight. Okay, so that's one direction of the theorem. What about the other direction? Well, first of all, let me go back to the previous statement, and let me reverse the arrow here. So we're going to do a proof by contradiction, which is very classical. It's an argument that's going to come up again when we talk about linear transformations. And we want to prove that we're going to prove something about linear transformations later, and the same argument is going to come up. So assume that's not the case, right? So assume, and to make things, I'm just going to say, well, assume that you have two equivalent metrics, but this relationship doesn't hold, right? So assume the two norms equivalent, but property star false. So remember, I'm not writing this down, but this is going to be a proof by contradiction. So the reason I'm assuming this is because I want to prove that it's inconsistent with assuming equivalence. So what is this saying, right? So let me actually do this. So I'm going to prove that what I'm going to say. Okay. I'm going to prove that if the metrics are equivalent, then you have this, and then a similar proof gives you the lower bound, right? So it can assume that if norm 1 and norm 2 are equivalent, then there exists a positive constant such this holds. And if you reverse the proof, you can get the lower bound here. So I'm just going to do one direction. Okay, assume that these two things are true. So if this is false, it means that for all c greater than 0, there exists a vector vc, right? I'm just negating this. For all c, there exists a vector such that the norm of v sub c is greater than c norm 1 is greater than c norm 2. This is for all c, right? Okay, just to it turns into a sequence, I'm going to say for all n natural number, right, I have a v sub n, such that v sub n of 1 is greater than v sub n of 2. Norm of v sub n of 1 is greater than n times norm v sub n 2. Okay, what do I do with this? Okay, now let me define a new sequence of vectors. Notice that by looking at this, I can tell, well, this is no negative, right? So I know that v sub n cannot be the 0 vector, because if it was a 0 vector, I have 0 here, inequality, right? So this cannot be 0. So the norm 1 of this vector is not 0. The norm 2 is not 0 either, because the vector is not 0. So let me define x sub n as vn divided by its norm v sub vn2. And now I'm going to divide here by something that's large, but not too large, with the square root of n. Why square root of n? Well, it basically needs to be a function that grows, but grows slower than n. And if I have this, you notice that x sub n satisfies the following equation, right? So I'm just dividing here. Here I have this ratio, norm of Vn according to 1, divided by norm of Vn according to 2. And, okay, you work it out, and you see that the norm of x sub n according to 1 is greater than, okay, here you get norm of this guy 1, divided by norm 2. This we know is greater than n. You divide by square root of n, so this is square root of n. But you get that the norm 2 of x sub n is, well, you have norm 2 here divided by norm 2 here divided by square root of n. So this is exactly 1 over square root of n. And now we have our contradiction. Why? Remember, assume that these two norms are equivalent, right? So now here I have a sequence of vectors that's going to 0 according to norm 2, right? So these vectors, I mean, this is the distance between x sub n and 0, and this distance is getting smaller as n grows. So it's going to 0. On the other hand, the distance between x sub n and 0 is not getting any smaller. It's actually getting larger and larger as n grows, right? So the contradiction I have is that I have a sequence that converges to 0 according to norm 2, but not according to norm 1. Therefore, it cannot be true that the two norms are equivalent, and this condition is false. You see? So again, right? So if the two norms are equivalent, this cannot happen. So it must be that this condition star is true. It must be that there exists a constant that allows you to bound the one norm in terms of the two norm. And by similar reasoning, you can show the reverse inequality. So this is it. So this is the only theorem we're going to prove about equivalence, well, outside of examples, right? The theorem says that if norms are equivalent because one is bounded by a multiple of the other. And that holds in both directions. And that's it for now. Thank you.